This video is an introduction to nuclear magnetic resonance spectroscopy. In nuclear magnetic resonance spectroscopy, or NMR spectroscopy, it is the atomic nuclei that are observed. And only specific type of atomic nuclei can be observed. Those nuclei are known as magnetically active nuclei. Nuclei, or a nucleus, atomic nucleus, may have a net overall spin. Nucleus is composed of what we call nucleons, protons and neutrons. And each proton and a neutron has a spin of 1/2. In a nucleus, they are arranged in energy levels, and those spins may or may not be paired up. If they are paired up, then they cancel out and net overall spin is 0. If they are not paired up, then there may be a net overall nuclear spin. So net overall nuclear spin, I, could be 0, 1/2, 1, 3/2, and so on, all the way up to 9/2. Magnetically active nuclei have net overall spin. Those that have net overall nuclear spin of 0 are not magnetically active and cannot be observed by NMR spectroscopy. So we can identify 3 types of nuclei. Those with spin of 0, and those would be nuclei such as helium-4, carbon-12, oxygen-16. So those are nuclei that cannot be observed by NMR spectroscopy. Then nuclei with spin of 1/2. Those are the most useful nuclei for NMR spectroscopy because they give relatively simple spectra that can be easily interpreted. Such nuclei are protium isotope of hydrogen, so hydrogen-1, carbon-13, fluorine-19, nitrogen-15, phosphorus-31. There are more, but these are most commonly investigated by NMR spectroscopy. And then we have nuclei with spin larger than 1/2. Examples of such nuclei would be deuterium isotope of hydrogen, so hydrogen-2, nitrogen-14. They both have spin of 1, and then boron-11, for example, has spin of 3/2, boron-10 spin of 3. These nuclei can be observed by NMR spectroscopy, but they give much more complex spectra. So they are not usually studied by ordinary researchers, but specialists in the field may focus on those kind of spectra and investigate those spectra in their work. Now we will only focus on nuclei that have a net overall spin. And we will look at the simplest case of nuclei that have a spin of 1/2. We will assume that spin is a phenomenon where a nucleus rotates around its axis clockwise or counterclockwise. We know that this is wrong view, that this is oversimplification, that's not actually what a spin of a subatomic particle is, but this is a good model and provides very good explanation and good predictions. So a nucleus is a positively charged species, and as a result of motion, rotation clockwise or counterclockwise around its axis, spin, it generates magnetic field. And that magnetic field can be represented as a vector of magnetization that is aligned with nuclear axis. In the absence of any external magnetic fields, those vectors of magnetization are oriented at random in all directions in space. When external magnetic field is applied, then these individual spins assume 2 energy states by aligning themselves either parallel or anti-parallel to the external magnetic field. In reality, they actually precess around external magnetic field, but we'll assume the most simplified case where they are either parallel or anti-parallel to the applied external magnetic field. And we can also represent that schematically like this, where initially nuclei have their magnetic vectors pointing in all directions at random, and then when external magnetic field is applied, they orient themselves either parallel, which is lower energy state, or anti-parallel, which is higher energy state. And there is energy gap. The energy gap between parallel and anti-parallel spin states is in the radio wave part of the electromagnetic spectrum. If one irradiates nuclei with electromagnetic radiation of the frequency that corresponds to the gap between the parallel and the antiparallel spin orientation, the energy is absorbed and nuclei jump into the higher energy level. Then once they are in the higher energy level, they relax and return to lower energy level. Then, since radiation is continuing, they again absorb electromagnetic radiation and jump into higher energy level, relax, and keep doing that over and over again. We call that process resonance. We say that nuclei are at resonance with external applied electromagnetic radiation. And so this is why this is called nuclear magnetic resonance spectroscopy. Nuclear because we observe atomic nuclei, magnetic because nuclei are placed in strong external magnetic field, and resonance because that's the phenomenon that we observe. Nuclei are at resonance with applied external electromagnetic radiation. The difference in levels between the two energy states is actually very small, and we'll cover that next. When magnetically active nuclei are placed in an external magnetic field, they assume two energy states, parallel and antiparallel. The energy difference between the two states is very small, and population difference of the two states is small too. So if we have, let's say, 1 million nuclei in higher energy antiparallel state, then maybe 1,000,001 or million, just a few nuclei will be in parallel state, in lower energy state. So very small population difference. The amount of electromagnetic radiation necessary for resonance depends on both the strength of the external magnetic field and on the characteristics of the nucleus that is being observed. When a more powerful magnetic field is applied, a higher energy radiation is required for nuclei to be in resonance. And then a spectrum of higher resolution is obtained. It means that the stronger the magnet, the more powerful magnetic field is, the more informative spectrum is, more information we can get from the spectrum because better resolution is obtained. Here in this table we have some magnets or magnetic fields. Their strength is expressed in Tesla. So 60 megahertz instrument on which proton nuclei are at resonance at 60 megahertz has magnet of a strength of 1.41 Tesla. Instrument like this is these days considered to be obsolete. Even instrument with 2.35 Tesla is obsolete. 4.70 is not sufficient for most purposes. That would be where hydrogen nuclei are at resonance at 200 megahertz. The instrument that is considered to be sufficient for practical work these days is 300 megahertz instrument. So instrument at which hydrogen nuclei are at resonance at 300 megahertz. And note that carbon nuclei are at resonance at different frequency, lower frequency. So typical good instrument, solid instrument these days that will be useful for research is one that has magnet of 14.1 Tesla and protons are at resonance at 600 megahertz, which means that carbon-13 nuclei are at resonance at 150 megahertz. And this graph shows that how with increasing strength of a magnetic field, the gap between parallel, which is shown by lower line, and antiparallel by upper line increases. So the stronger the magnetic field, the larger the gap, and that means the larger the resonance frequency. NMR spectrometers, as you have seen from the terminology I have been using so far, NMR spectrometers are commonly designated by the frequency at which protons are in resonance, rather than by the strength of their magnetic field. So, for example, NMR instrument is called 60 megahertz instrument, 250, 600 megahertz instrument, NMR, even if we use that instrument to observe carbon-13 or other nuclei. So we always designate instrument based on the frequency at which protons are at resonance. We do not designate it by strength of magnet or by frequency at which some other nuclei are observed. So we say that spectrum is taken, let's say, on a 400 megahertz instrument. Now, when we report carbon-13 NMR spectrum, we will say that it was 100 MHz instrument. We have just seen that nuclei of particular isotope, of particular element, are at resonance at certain frequency depending on the strength of the applied external magnetic field. Based on that, we would expect all of those nuclei to be at resonance at the same frequency. But actually, the situation is slightly more complex, because nuclei of the same isotope, of the same element, may have slightly different chemical environment. Chemical environment means neighboring bonds and neighboring nuclei. Those neighboring bonds, of course, have electrons, charged particles, which are moving, and of course there are neighboring nuclei with their own spin or spins. They also generate their own magnetic fields. They may be small, but nonetheless they generate their own magnetic fields. And those individual magnetic fields may either reinforce external magnetic field, that means they will be de-shielding nuclei to the external magnetic field, or they may oppose external magnetic field and shield nuclei from external magnetic field. That means that each individual nucleus experiences what we call effective magnetic field. And effective magnetic field is applied external magnetic field minus local magnetic field, and local magnetic field is sum of all the individual magnetic fields generated by the neighboring bonds and the neighboring nuclei. So local magnetic field, some of it may either shield or de-shield the nucleus to the external magnetic field. Another important property of spectra, of NMR spectra, is chemical shift. Since frequency at which nuclei are at resonance depends on the strength of the magnet or the applied magnetic field, that means that whenever we take a spectrum, if we are to take it on different instruments with different magnetic fields, resonance frequencies of individual nuclei would have been at different frequencies. And it would be very difficult to compare spectra taken at different instruments. For that reason, we have introduced concept of chemical shift, where we have eliminated frequencies and chemical shift is the same for all the NMR spectra regardless of the strength of the magnet. Chemical shift delta is defined as frequency of sample minus standard frequency, frequency of a standard, divided by frequency of standard. So that it's dimensionless unit. Since we have frequency units divided by frequency units, they are in hertz, hertz cancels out, we have dimensionless unit. The number that we end up with when we subtract frequency at which sample is at resonance minus frequency of standard divided by frequency of standard is a very small number. To end up with manageable, approximately whole numbers, we multiply that number by 10 to the power of 6, a million. And so the original numbers are actually parts per million. And so we sometimes use parts per million as units for chemical shift. Standard is tetramethylsilane, or TMS. Tetramethylsilane is extremely useful as a standard because, first, it has 4 methyl groups, that means 12 protons. 12 protons are identical and they give very strong signal because there are 12 of them and they are the same. It's one signal and it's very strong. So we have to use only small amount of standard to obtain a signal. In addition, it's relatively unreactive, so it won't react with any of the potential samples of the compounds we are studying. It has very low boiling point, only 28 degrees Celsius, so it will evaporate very easily, and that means it can be easily removed after spectrum is taken. It can be easily removed from the sample without contaminating that sample. Here we have a proton NMR of ethanol. Note that in ethanol we have 3 types of protons. They are labeled here as A, B, and C. So methyl group has 3 identical protons. They're labeled as A. Then methylene group, CH2, has 2 identical protons. They're labeled as B. And finally, there is proton attached to oxygen, C. And note that in the NMR spectrum, We also have three signals. They are A, B, and C. They are indicated as each signal belonging to a particular proton. So signal belonging to methyl group is shown in spectrum as A, and then it's slightly above 1. Then one belonging to methylene group B is around 3.5, and one belonging to hydrogen attached to oxygen is around 2. So you can see that number of signals corresponds to number of chemically different types of protons in a molecule. So from the number of signals, we can draw a conclusion how many different types of protons are present in an organic molecule. At this point, you should ignore splitting of signals. So for example, signal A is split into 3, signal B into 4. You should ignore that. We'll cover splitting of signals later. It is still one signal. Even though it may be split into a multiplet, it is still one signal. And finally, one other point related to chemical shift that we have just covered. We can look at that now because we are looking at the actual spectrum. We define chemical shifts as being downfield if chemical shift is higher chemical shift. So for example, we will say that signal due to protons B due to methylene group is downfield from signal due to hydroxyl group, hydroxyl proton, proton C. And of course, conversely, lower chemical shifts are upfield. So signal A due to methyl group is upfield compared to signal due to proton of the hydroxyl group C. Here is a list of chemical shifts that are commonly encountered in organic compounds. If possible, you should memorize this list. So simple hydrocarbon protons absorb in the region of between 0.5 and 1.5 ppm. Protons on carbon that is adjacent to a carbonyl group absorbs around 2.1 to 2.2 ppm. That's very characteristic absorption and shows often on exams. Electronegative atoms such as oxygen or halogen shift absorption on protons attached to that carbon to around 3 to 4 ppm. Alkene protons absorb in the region of 5 to 6 pm, aromatic protons between 7 and 8 pm, aldehydes around 10, that's very characteristic. Hydrogen attached to carbonyl group is around 10 ppm, that will be aldehydic proton, and finally protons of carboxylic acids absorb around 12 ppm. Nuclei that are chemically equivalent are also called magnetically equivalent for the purposes of NMR spectroscopy. The amount of energy of a particular frequency that is absorbed depends on the number of magnetically equivalent nuclei, because they absorb at the same frequency. Such protons, of course, share the same chemical environment, and of course they have the same chemical shift. The area under the peak is directly proportional to the number of protons that give rise to that peak. So that's called integration. So when we consider a spectrum of ethanol that we have already seen, we have three types of protons, protons A, B, and C that we have already seen. And in this case, an integration curve has been superimposed on the spectrum. An integration curve, this is an older way to represent integration curve. These days, actually, computers do the integration of a signal and simply print a number above or below. This is the older way to represent integration curve, where a pen would simply plot integration curve and deflection of the pen would integrate the area under the peak. So the amount of deflection of the pen would correspond to area under the peak. And we can determine for example, protons A, we draw a line where the original level of the pen is and then how much pen was deflected, and we measure that height, and we can see that this amounts to relative area of 3. Then when we look at signal due to protons B, again we follow the same procedure, original level of the pen, how much it was deflected, and that corresponds to relative increase, relative height of 2, integration of 2. And finally C, follow the same procedure, its relative integration of 1. So we can see that going CBA, that relative integration is 1, 2, 3. and that corresponds to number of protons. So integration of NMR signals corresponds to relative number of protons, or relative number of nuclei that give rise to a particular signal. The way we carry out integration is we simply measure, as shown here, the amount of deflection of the pen, the integral under the curve. And then, of course, these numbers are not usually 1, 2, 3. They may be 7, 14, and 21. Then we divide all those numbers with the smallest number, and that's how we end up with the smallest ratio of numbers. And that smallest ratio of numbers gives us the relative number of those types of protons in a molecule. In this case, it is 1, 2, 3, and indeed, in molecule of ethanol, we have A, B, C protons in that order in the ratios of 3 to 2, 1. But that's the smallest possible number. In actual molecule, a ratio may have been different. It may have been 6 to 4 to 2, or some other multiple of those smallest possible numbers. This completes introduction into NMR spectroscopy, and next we are going to look into signal splitting or coupling in NMR spectroscopy.